Okay, most likely we're going to go over this in class, but I thought I'd post it as well so that you could go over it again if you'd like. So what we have as we're moving into chapter 7, we're looking at how the periodic table was developed as well as how it's organized according to the behavior of individual atoms, and that's really related to the electron configuration, where the outer electrons are, and how those interact with other things. So when we think of the development of the periodic table, early on there were certain compounds that had a continuing or had similar properties, and so organizing those elements with one another seemed a logical step. So using their chemical properties was more important than utilizing their physical properties, if they were solid or liquid or gas, or color or hardness. So those things, they might have some similarities, but it definitely wasn't a strong enough connection to be able to really organize materials. So when Dmitri Mendeleev and Lothar Meyer made their different organizations of materials, what they did is they grouped them together, typically first starting by utilizing atomic mass and kind of organizing it by that, but then moving and shuffling things around so that things that had similar properties were in the same groupings or the same columns. And this graphic, I like this picture of the periodic table because it gives an idea of at what time periods we actually learned or discovered these different elements. You know, some were around for a very, very long time as far as our knowledge of them. So if you think of ancient times, you've got iron, you've got copper, you've got silver, gold, mercury, tin, lead, um, carbon, and sulfur. So those, and that would be really because all of those compounds you can find in their pure form, either by mining or a variety of other ways to access those things. Many of the other compounds that were discovered later on had to be kind of isolated from the compounds that they were formed with. So if you think of the alkali metals, they are all very reactive, so the likelihood you're not going to be able to dig down in the earth and find like a lump of lithium or a lump of potassium, because it's highly reactive with air and oxygen, and so it wouldn't just exist as the pure element at that point. So when Mendeleev organized his periodic table, he noticed that among other things that there were gaps, that there was something, there were elements that had yet to be discovered, but he predicted that there should be something in certain spots. So one of the examples being germanium, which he called ecosilicon, because it is just below silicon in his periodic table as well as in our current one. And he proposed that it had, he was able to kind of predict its mass and some of its properties because of the column that it would have been in. And lo and behold, later on, it was discovered and found to fit right into that spot. So, yeah, really kind of cool. And the periodic table has continued to be a very useful tool in predicting properties, in deciding what could be a good alternative when thinking of, let's say you utilize a certain element to be a catalyst in a reaction, or you are trying to make a compound that has these certain properties, and you know that one compound has similar properties, and so you utilize other elements within that group to get this similar reactions or products. So this chapter will look at some of these trends that the periodic table you can use to map out. So one is like the size of atoms and ions, how those are positioned on the periodic table, as well as like an ionization energy and electron affinity. So, but to start with it, we need to think about like the outer electrons and how they relate to the inner electrons and, of course, the nucleus. So electrons are attracted to the nucleus because of all those protons, that positive charge, electrons are negative charge. So there's an attractive force, but there's also a repulsion because all the electrons are negative and they're all surrounding the nucleus. And so there's kind of a repelling relationship as well, where the electrons don't, they're trying to find a space around the nucleus that's as close to the nucleus as possible, but also repelling that negative charge as well. So when we go to calculate what is called the nuclear charge, um, we're basically looking at those two factors. So how do the inner electrons shield or impact the outer electrons' attractiveness to the nucleus, which would be, so that's the effective nuclear charge, or ZF. So it's found basically by taking Z minus S, where Z is the atomic number. So in this case, we've got atomic number 11, which is sodium, and then we subtract an S value, or the screening constant, which for our purposes, at least for right now, we could just understand that to be the number of inner electrons or core electrons. So for sodium, the effective nuclear charge would be +1. Okay, and as we go into this deeper, we'll see how that impacts, like how the effective nuclear charge impacts the overall size of the atom, how easy it is to ionize it, how strongly it attracts other electrons, its electron affinity. So we'll kind of explore this a bit more as we get into it.